Let us take a look at this hefty problem. A typical raindrop is much more massive than a mosquito and falling much faster than a mosquito can fly. How does a mosquito survive the impact? I don't know, let's find out. Recent research has found that the collision of a falling raindrop with a mosquito is a perfectly inelastic collision. What does that mean? What does perfectly inelastic collision mean? It just means that when the raindrop collides with the mosquito, they stick together and eventually the mosquito reaches the same speed as the falling raindrop, and momentum is conserved. That is, the mosquito is swept up by the raindrop and ends up traveling along with the raindrop. Once the relative speed between the mosquito and the raindrop is zero, the mosquito is able to detach itself from the drop and fly away. How very ingenious. A hovering mosquito is hit by a raindrop that is 50 times as massive and falling at 8.4 meters per second. That's a typical raindrop speed. How fast is the raindrop with the attached mosquito falling immediately afterward if the collision is perfectly inelastic? So just assume the mosquito is just hovering and the raindrop hits the mosquito. So would the velocity of the falling raindrop be more or less? I'm going to say it's going to be less, since its mass would have increased because you'd have to put the mass of the mosquito on the raindrop and so its velocity would have consequently decreased. But we are asked to find the velocity of the raindrop. So let's do that first. So from the conservation of momentum law, we should say that the initial momentum, let's just say P1 equals to P2. So the initial momentum is, we're just dealing with the raindrop by itself. So we'll do the mass of the raindrop times the velocity of the raindrop, which would be equal to the mass of the raindrop plus the mass of the mosquito times the velocity of the raindrop plus the velocity of the mosquito. So the mass of the raindrop is 50 times, right, so the raindrop is 50 times as large as the mosquito. So we'll say the mass is 50 in this case. The velocity is 8.4 meters per second. And since the raindrop is 50 times the mass, so we'll call the mass of the mosquito 1. So the mass of the raindrop plus the mass of the mosquito will be 51 times the velocity of the raindrop plus mosquito. This is what we're trying to find out. So essentially you just bring this 51 down here and you can find out the velocity final. That means the velocity of the raindrop with the mosquito attached to it. So we just do 50 times 8.4 over 51. So what does that give us? 50 times 8.4 divided by 51. So that gives us a velocity final of 8.2 meters per second. So that's what the question asked of us, and that is what we found out. Second part of the question is this. Because a raindrop is soft and deformable, the collision duration is relatively long, 8 milliseconds, sorry. Because a raindrop is soft and deformable, the collision duration is relatively long, around 8 milliseconds. What is the mosquito's average acceleration in G's during the collision? The peak acceleration is roughly twice the value you found, but the mosquito's rigid exoskeleton allows it to survive accelerations of this magnitude. In contrast, humans cannot survive an acceleration of more than about 10 Gs. So mosquitoes can survive accelerations of much more than 10 Gs. Let's figure out how much more. So we know that acceleration equals to acceleration A equals to the change in velocity over the change in time. We know that the time was given to us as 8 milliseconds. So 8.0 times 10 to the negative 3 seconds. That's 8 milliseconds. And we found out from the previous part of the question that the velocity, the final velocity with the mosquito and the raindrop together was 8.2 meters per second. So 8.2 meters per second minus our initial velocity, which is 0. This is coming from the point of view of the mosquito. So if the mosquito is hovering and a raindrop hits it, its initial velocity in the downward direction is 0, because the mosquito is not flying downwards, it's just hovering. When the raindrop collides with the mosquito, that time of the collision is relatively long because it's perfectly inelastic. The mosquito sticks onto the raindrop, so this is that collision takes 8 milliseconds, and the final velocity after it collides with the raindrop is 8.2 meters per second. So acceleration is essentially velocity final minus velocity initial over time. So when we calculate this number, we arrive at a number. Let's find that out. So the acceleration is 8.2 divided by 8. So it's 1.025 times 10 to the 3 meters per second square. But they've asked to find out this value in Gs. So we essentially divide this acceleration by 9.8, which is the acceleration due to gravity. So in Gs, 1025 divided by 9.8 would give us 105, approximately 105 Gs. So due to the mosquito's rigid exoskeleton, it can survive an acceleration after a raindrop hits it of 105 Gs. That's huge.